material to a final product as a pathway. So in a pathway, you have multiple enzymes that carry out or facilitate or catalyze different conversions of the starting material step by step by step, as you know, till you get to the product of that pathway. And a pathway may be linear, like that. It could be branched, or it could be cyclical. Can you think of an example of a cyclic pathway? Pardon? We're talking about metabolism. So reproduction is going to cut it. So can you think of an example of a cyclic metabolic pathway? Krebs cycle, citric acid. All right, I'm not going to go into these concepts about free energy in as much detail as you cover them in chemistry. So I'm going to just use the term G for free energy. But if you talked about this in chemistry, you probably recognize they, usually designate the free energy of formation of a particular chemical under certain standard conditions and that sort of thing. Well, I'm going to keep things very general, and I'm not going to belabor or burden our discussion with the topic or with, talking about standard conditions. I just want you to recognize that under a particular set of conditions, if you have a change in free energy such that if you have a starting material, let's say, for example, A goes to B, and the free energy in B is 100 kilojoules, and the free energy that was in A was 50, what kind of reaction is that? Exergonic or endergonic? Didn't hear you.
Exergonic.
How could that be exergonic? You got more energy in the product than you had in the starting material.
Endergonic.
Yeah, that's the only other choice. But if we figured out delta G, 100 minus 50 is 50. So delta G is positive. That means you had to put in energy to get from A to B. In contrast, if you went from A to B, and A was 100 and B was 50, then 50 minus 100 is minus 50. So what kind of reaction is that? That's exergonic, because you're getting energy released. Okay, so either you're not awake or you need to review these concepts. Or maybe, a few of you need to review these concepts. So just kind of refresh yourself on these sorts of things. So if you've got more energy in the product than you had in the starting material, like here, that energy had to come from somewhere. And cells generally will take, they might get that energy by hydrolyzing ATP, for example, and coupling that hydrolysis with this sort of a reaction so they have some energy to have some input to make A go to B, right? Because we recognize ATP as the energy currency that's usually used by cells. Here's the structure of ATP. These bonds that are shown in the wavy, with the wavy lines are the high energy bonds, particularly the one between the second and third phosphates, right? So when that third phosphate is cleaved off, energy is released, and vice versa, if the cell wants to make ATP from ADP and inorganic phosphate, it's going to have to get energy from somewhere in order to do that. And, in bacteria, one way they can do that to make ATP is to use their proton motive force. And in regular cells, if they have mitochondria, they can, do the same thing. All right, we come now to the synthesis of ATP. We're going to talk about 3 ways that cells can make ATP. The first is substrate level phosphorylation, where the energy inherent in a high energy bond is used to drive the synthesis of ATP. And here what they're showing is a situation where you have a phosphorylated compound and you have a high energy bond, and this phosphate is added to ADP to make ATP. As you know, substrate level phosphorylation occurs in different pathways. It occurs, for example, in glycolysis, and we'll look at that a little bit later. The second type